lecturer is going to be Christian, and he's going to kick off the school with the first lecture on CFT basics. Okay, go ahead.
Yes, thank you very much, Satya. Thank you very much for the invitation. And I hope that for the students, this is going to be a very pleasant ride through some basics of CFT. First, my name is Christian Northe, and I am a postdoc at Ben Gurion University. And I work mainly with high energy stuff and have done some work with conformal field theory also. So I will start sharing now. Let's go. And please feel free to ask questions and interrupt. I won't be able to monitor the chat, so just speak up. Just speak up in case Saskia, if you see some questions in the chat and I just overlook them, please just let me know. Okay, so let's get started. Can you see my screen? I think so. The question is,
yes, we can see your screen.
Like this. I guess that's better.
So just to check, like, people, you can mute yourselves, right? Like,
yes, we can.
Okay, thank you, Alejandro.
Okay, cool. So I think this is better for the screen than the other one, right? At least on my PC, this if I tilted the
it looks better like this.
Okay, good. Thank you so much. All right, good. So this is going to be an introduction to conformal field theory, which is usually referred to as CFT. And in a moment, I'm going to start writing. No worries. So for like the first like introduction, I'm going to just talk. I have prepared one slide, if you will, with applications. So there are some traditional applications that made CFT what it is, where CFT basically earned its name. The most foremost one is the one of critical phenomena, quantum critical phenomena. That's this one here, where in the 80s people realized that phase transitions, in particular of second order, could be described by conformal symmetry, which was very, very striking because the conformal symmetry that people were studying was infinite dimensional. So it was perplexing that such a powerful symmetry, something as exotic as an infinite dimensional symmetry, would actually govern a physical system. Then there were applications to deep inelastic scattering. More prominently, those are applications which are still done today in string theory. Then in condensed matter, there was the Kondo effect, where conformal field theory was also very, very influential and important in discovering the underlying structure of that. But those are all, say, traditional applications that I don't want to talk about too much. Actually, I won't talk, for now, I won't talk too much about applications. But the school that we're about to embark in has many, many interesting topics, which are modern and which you should learn in their own right, because they're very interesting, as I said. And CFT plays a more or less important role in all of them. So for instance, Chern-Simons theory has a relation with conformal field theory. So when you put a Chern-Simons theory, that's a three space-time dimensional, so 2 + 1 dimensions. When you put that thing on a manifold with a boundary, on its boundary, this thing is going to develop critical edge modes, critical in the sense that they are conformally invariant. But we'll learn about that in the main school, in the main bulk. I'm also going to talk about boundaries. That's what I'm going to talk about, boundaries and defects, mainly in conformal field theory, and that reverts to applications like the Kondo effect that I mentioned. It reverts also to modern applications in topological phases of matter, which I won't be able to talk about, but maybe they'll be shown in the part taught by Hotat Lam on non-invertible symmetry. Then there's going to be also a class on topological insulators, and that comes basically, it comes back like in the context of CFT. the Chern-Simons and the topological insulator part, they together, so they give rise to an application of conformal field theory. And then there's topological quantum computation, where CFT itself is not really, to my understanding, as present, but there are concepts like fusion and braiding and so on that were developed also by the community of conformal field theory, and which are now finding widespread application or are very central in the field of topological quantum computation. So these are all very good reasons to, first of all, to come to this school, because these are modern topics and very interesting. But there are also very good reasons to learn conformal field theory. And that's the point that we want to address here in this preschool, at least in this part of the preschool. So I have typed up a bunch of notes. You can find them already in the overleaf. I should say that I have typed much more in the notes than I can possibly present in the 6 hours of preschool that we're going to go through. And depending on how many questions you ask, I'm going to go slower or faster. So I can't promise to cover everything. Though I would like to, so my aim for this school, for this preschool, is to convey the idea of a conformal group and a conformal algebra, in particular in 2 dimensions. So this is going to be in particular in 2D. I want to tell you how to think about fields, in particular their relation to states in a conformal field theory. And importantly, what I need for the school itself is fusion. So the concept of fusion is one thing that I want to highlight, and how state spaces in CFT are being constructed. So basically, if you want to follow the boundaries and defect part, what you'll need is, for instance, the fusion and the CFT state space section. So that comes toward the end. And the first 2 parts are sort of built up. And from what I understand, it's also important for like non-invertible symmetries and so on. So we'll be talking about stuff like Verlinde lines and so on, but that's all for the future. So far so good. That's as far as the introduction goes. And now, if you have any questions up until this part, please speak up. And if not, let's just indulge in CFT, in conformal field theory. Okay, so feel free to ask any questions. This is being recorded. Also, so if at some point I go too fast and you don't dare to ask questions and so on, you can always watch the recording, but take advantage of the opportunity of me being around and just ask questions. So the first thing that we want to discuss is the conformal group and its algebra. Okay, so the aim of the section, as I said, it's also typed up, but the aim of the section is to first get acquainted with conformal transformations, and the conformal group. So that's what we want to do. And in particular, this first part is going to be short, but we're going to talk about the conformal group, how it is, so to say, in general dimensions. In particular, it's going to stay like that in d equals 3, bigger than 3, bigger or equal than 3. And for d equals 2, we're going to have some extra words to say. But for now, let's not worry about anything additional, and let's just get started. So the conformal, so the first point is 2.1, and it's going to be conformal symmetry. Symmetry in D bigger than 3, equal or bigger than 3. Okay, so what we're going to start with is 2 manifolds. So I should say, for those of you who are not too familiar with manifolds, it's not super duper important to know what a manifold is. From what I understand, the background is condensed matter physicists, and I don't know how much you've been exposed to this kind of material. So on a manifold, I'm going to draw a picture in a moment. So to make this sentence here clear, so there is a map F between these two manifolds. So what you should think of this as is like you have this is going to be some blob. This is going to be the manifold M, and on this manifold you can install a set of coordinates, and let's call them x mu. And then you have some other blob, that's the manifold M twiddle. And on this manifold, you can install a set of coordinates y alpha. So these don't need to have the same dimensionality, but for our purposes, it's going to be the same, actually the same manifold. But for now, let's keep it general. And I said there's going to be a map F. And there is a notion of measuring distances. So distances are measured on M by the metric G. And then the same is on N twiddle by G twiddle. So if you have a distance from here to here, you measure that by G. And similarly from here to here, you measure that by G twiddle. And now what you can do by virtue of the map, you can relate. So this is called something called the pullback. It's denoted F subscript star. The details are not super duper important, though you'll see in a bit what the details are. And what this means is that you can take the metric on one manifold. So you can take the metric G twiddle, and you can pull it back. That means you apply this map F subscript star, and you return, basically what you get is you get the metric of M, right? So this here is on M twiddle, and this here is on M. But you actually have some freedom if we want something called a conformal transformation. So this is, let's call this lambda of, not of x yet, lambda G. So F is called conformal. F is conformal if it satisfies a relation of this type. That means, like I said, the distances are basically only being rescaled by a positive smooth function. So let's make that clear. So lambda is a smooth, that means you can take derivatives at will, smooth function, smooth and positive function on M. Okay, so what that means concretely, come on, here we go. What that means concretely, so this was very abstract, I believe, up until now. And now, what that means concretely is that you can take the metric tensor, it's going to have some indices alpha and beta, and you do a coordinate transformation between the two, looks like this, and you return to lambda of x and G mu nu of x. So this is a very concrete prescription of how to think of a conformal map. Okay, so one thing that I'm going to do throughout this lecture is that I'm going to sprinkle exercises that you can do. I encourage you to do them because they give you some an understanding of what's going on. Usually they're very simple exercises, so you shouldn't. They're intended to make you think about the concepts, and once you understood the concept, it should be very straightforward to execute the exercise. The first exercise that I propose here. So this is exercise 2.1. So you're supposed to show that conformal transformations are locally angle preserving. Angle preserving. That means that you have something like, let's take a grid, and a conformal transformation could do something like this to your grid. That means in particular that the angles here and here, my drawing is probably not very good, but the idea is that the angles are supposed to be the same locally. Evidently, my drawing is not very good, but you get the idea. We're not here to do art, we're here to do physics. Okay, so I provide the formula. The formula for angles is in the notes, so I won't write that down here because we won't dwell on it for too long. But you can go and look at the overleaf, and there you'll find exercise 2.1, and there is an expression for the angle. Expression for angle in the notes. This is also evidently, so I want you to poke at the notes. So I will do this here and then. Most of the time, though, I will write concrete expressions. Okay, so is there a question?
Yes. How is the pullback related to the function f?
Oh, thank you. Very good, very good. So the function, what we're going to do is basically we're going to declare y is the function f of x. So basically we're going to take these coordinates and declare them to be the function f of x. And to give you an idea, I'll give you an exercise in one minute, which is more concrete. Did that help with the question, by the way?
I guess implicitly it will help.
Okay, good. So there's going to be one exercise / example in 1 second. So what we're going to do, so before I said that we have these manifolds, these blobs n and m twiddle, but I'm going to be much more concrete now in order to work. We're going to restrict to m twiddle and m to be the same. And moreover, we're going to restrict it to be r p comma q. That means that you have just like Minkowski space has one temporal coordinate, and several, say 3 + 1 dimensional Minkowski space has 3 spatial coordinates and 1 temporal coordinate. We are going to allow for p temporal coordinates. That means that the metric that you're going to have, actually let's not write diag, it's going to write -1, then there's going to be a bunch of zeros here. There's going to be a bunch of zeros here. There's a -1, -1, and then there is 1 up until the end. And we're going to have, they're going to be p times -1, and Q, let's just write it in this form. Diagonal of -1, da da da, -1, 1, da da da, 1. Here's P, and here's Q. For all practical purposes, we're actually just going to stick with Minkowski space or full Euclidean space, where you just have well, conventional simple things. So one example, and that's another exercise. Exercise 2.2 is you should check that the inversion, and the inversion is defined as follows. I'm going to write curly I, and it takes x to y of mu. And so this is now basically f of x, and this is x mu over x squared, and x squared is eta mu nu x mu x nu. So check that the inversion is conformal. Okay, so to give you an idea of what the inversion does, so suppose you have this is your coordinate system in 2 dimensions. Let it be Euclidean for now. And there's a unit circle. So there's a unit circle. Here's 1. And the inversion, what it will do is it takes a point from the inside of the unit circle and it maps it to the outside of the unit circle. So this is I. And vice versa. So if you take a point from the outside of the unit circle, it will map it into the inside of the unit circle. That's what the inversion does. So that's an exercise, and what you're supposed to do now is you have this prescription here, and what you're supposed to do is you're supposed to go into this formula here and check that you return that basically you get from. So you're supposed to take here this metric eta, and this metric eta, and plug that thing basically in here and just evaluate these coordinate transformations. And you should get a prefactor lambda. That's what you should find. Okay. So far, I have only provided a definition for a conformal transformation. I've told you that they are angle preserving. That's just a property, and you're going to check that property in an exercise. And then we've seen an example of a conformal transformation, which you're also going to check that it is actually a conformal transformation. It shouldn't be too difficult. For those of you at least who are familiar with these index notations, it should be super simple. If not, it's actually also a good exercise to familiarize yourself with x mu, y mu, and so on, like these notations. Okay, so if so there's this statement that the conformal group, well, it's a group, conformal transformations form a group. That means that you can also find a sort of quote unquote basis for conformal transformations, meaning that you can take any conformal transformation and you can rewrite that as in terms of generators, meaning as a set of basic transformations. And they are the following ones. So So I add, first of all, a sequence of 4 types of transformations. So, which are those? So I'm going to make a little table. So they're going to be transformations. Let's see how much space I need. The first example is a translation. Why is that? I'm going to give the translation a name. I'm going to call that T. Well, what does a translation do? A translation takes a coordinate x and it maps the coordinate x into x plus a constant. So here this is a constant for vector, Lorentz vector. And you can just check that this is maybe something that I didn't declare as an exercise, but if you take del x mu plus a mu and you take a derivative with respect to x nu, you just get delta mu nu. And that's the kind of stuff that you're supposed to do in order to check that it's a conformal transformation, because you're supposed to check this relation here, that is defining a conformal transformation. Okay. All right. So this is the action of the. So this is the action, and let's keep going. So then another thing that we have are rotations. Rotations including boosts. So these are expressions which are of the type r mu nu x nu. So these are rotations by a matrix. And so I'm gonna make another column here to indicate to you how this is supposed to be read. So this, as a matrix equation, what you get is r eta r equals eta. So this is what a rotation does. So the metric doesn't rescale. Distances don't become different. They actually stay the same. It's just that they're being rotated. So this means lambda is 1. Here we also had lambda being 1 by virtue of this thing. Let's move it down. So these are conformal transformations, and you recognize the first two. Those are the ones, like if we're working with special relativity, we have Lorentz boosts, we have Lorentz rotations, right? And those are of this type. So usually we call them lambda. It's just that in this case I called something else lambda, so I'm calling these transformations R. So you see that this has the structure. So in particular, the Poincaré group, which consists of translations and rotations, is a subgroup of the conformal group. And the conformal group has another two types of transformations. And then the first one is the dilation. And the dilation, something that doesn't change angles, like you can just scale a coordinate by a constant lambda, right? So that's the idea that I can take my grid and now I just make it bigger. Right? So that's a conformal transformation. It preserves angles. Just like translations, right? Translations just move this thing. Rotations just rotate this thing, and the angles are all preserved. So those are very intuitive. And then there is one which is called special conformal transformation. Special conformal transformation. And this one is not as intuitive. This one is not as intuitive, but we've just learned about the inversion. And the inversion, what it does is it takes, let's see, we had a unit circle, and a point from the inside of the unit circle is taken by the inversion to the outside, but it turns out that it's useful to actually take another translation. So this is a translation, so this is an inversion. Translate this thing and take it all the way back by another inversion. So what the inversions are, what the special conformal transformations are an inversion followed by a translation followed by an inversion. And you can check that these are also conformal. Why not? The reason when one doesn't take the inversion as a generator, well, one reason is that that it doesn't. Well, the simplest reason is that one needs still d degrees of freedom as generators, and translations provide that. By that I mean, well, actually I didn't explain this yet, but the conformal group will have a certain dimensionality, and one will see that inversions don't make up all of them. We see that by composing with translations, we actually get the full lot. So in these special conformal transformations induce a transformation which is x mu. This is a bit longer. I hope you've left space. 1 plus b dot. B dot x dot is the scalar product with the metric. And so this is the special conformal transformation. We won't dwell on this one for too long. You should just be aware that it is around. So in general, let's count the number of generators. Generators. So we have d translations. So this is t. We have now I got to cheat. I think d minus 1 over 2 rotations. And then we have 1 dilation, so that's d. And we have another d special conformal transformations. All right, so in total, now let me look up. We can do the calculation here, but let's just look it up. We have d plus 1, d plus 2 divided by 2 generators. So these are the generators. And something that I'm not going to show in detail, I'm just going to basically heuristically argue now. I'm going to pop out the head. So this is the dimension. This is the dimension of a Lie group, and that Lie group is SO P plus 1, Q plus 1. So it looks like, so the conformal, so this, it turns out, so this, let's actually make the statement concrete, that the conformal group in D bigger or equal than 3 dimensions is precisely that. Oh, let's be clear, on RPQ is SO P plus 1, Q plus 1. So actually showing this will take us a bit too far afield for the applications that I have in mind, or for the things that I have in mind that I would like you to know before entering the school. So I'd rather just leave it like that and just tell you that this is like sort of a true statement, and I won't really derive it. Those who are interested in the notes, I have provided a bunch, like 4 references. Those are my 4 favorite references to learn conformal field theory, and I would just let you sort of, I would suggest that you go and learn it there. Okay. So far so good. Yep.
Hello, I have a question regarding coming back a bit for the special conformal translation in the definition of it. B mu, sorry, I'm thinking as a physicist only, but B mu is exactly like the inverse of X mu in units. So what is exactly B?
B is basically a translation. Let's see the units. These expressions in conformal field theory, everything should be scale invariant. So B should carry here the inverse of x squared. Let's see. But that doesn't quite. So you see that most likely here there may be some units missing, but the idea is that B is basically this translation here. So let's see, what are the units of this thing?
Should be inverse of length. Then you'll have length plus length divided by something which is dimensionless.
Yeah, probably.
Yes.
Yeah. I'll think a bit about
Right.
that. Like with units, I am very slow.
Okay.
I tend to not touch on them. But in principle, yes. So the idea is also always that in conformal field theory, you work with dimensionless objects. So you would ideally like to think also of x and so on as being scaled or like divided by some length scale. Suppose if you have like a finite system, then you have a length scale L, and then you want to divide all of your coordinates by that. Okay. All right. So thanks for the question. So the next thing, so starting now, pretty much, I will restrict to D equals either 1 plus 1 or D equals 2, meaning either Minkowski space 1 plus 1. Actually, I'm mostly going to restrict to Euclidean. Let's just be frank. Mostly, I'm going to restrict to Euclidean, to the Euclidean case. So, but in the literature, when you talk about two-dimensional CFT, you find the conformal group, the global conformal group, I should say, of 1, 3 or SO2, 2. Okay. So the next thing that we want to talk about is, well, the conformal symmetry in 2 dimensions. Maybe I shouldn't say like let's spell symmetry out, just for like that. Okay. So the aim here is to get acquainted with the conformal algebra in 2 dimensions. We're going to see that something special is going on here. So we want to do this classically. And the buzzword for this is the Witt algebra. Oopsie, algebra. And we're also going to do this, well, we're not going to derive this most likely, there is no time for this, but we're going to talk about the quantum version of this, which is the Virasoro algebra. We'll see how much I'm going to say about the derivation of the Virasoro algebra. I'm going to try at least to motivate it, but we only have 6 hours, and mostly the school is not about the details of conformal field theory, but I want you to get up to speed with the idea of conformal field theory per se, so that you can follow later on in the school. And the other point that we're going to touch upon is the relation to the energy momentum tensor. The energy momentum tensor in this setup. So it's actually going to take a very central role, like usual, but this time, actually, you're going to see that it's extremely central. It's basically the protagonist. All right, so let's start with 3.1, and this is called something global conformal transformations. And I'm going to explain to you what I mean by global. So all the transformations that we talked about just now, meaning translations, rotations, dilations, and the special conformal transformation, they are defined basically everywhere on your manifold, and we're going to call that global. We're going to see in a moment that this distinction makes sense. But for now, basically, by comparing with the section that comes after this, we're going to see how this makes sense. So for now, don't worry too much about the epiphet global. We'll see how that comes in. So we're going to stick with, from now on, we're going to stick with Euclidean signature. We work with Euclidean signature, meaning that we have a manifold, like I said in the beginning, which is not going to be Minkowski space, but just good old R2. And so we're going to equip R2 with coordinates x mu, and these coordinates are called just x0 or x1. But certainly we can also, so that this thing here is, it's not a 2, it's just this symbol here written from up to down. We can also think of R2 as the complex plane, and then we can parameterize the complex plane by a complex coordinate, which we're just going to call x0 plus I x1. Okay. So now we can go back to the table that we had before. Before we had d dimensions, and now we can be a bit more concrete. So the conformal transformation, I'm going to again draw a table, the same table as before. So there's the conformal transformation, which are translations T, rotations R, the dilation D, and the special conformal transformation, which I'm just going to write special. Then we had an action. So the action for translations in complex coordinates, we have this complex coordinate z, and this thing is just going to be mapped to z plus a, where a carries two real degrees of freedom. Or one complex degree of freedom. Then the rotation is just, well, rotating by a phase. And phi, if this wants to be an honest rotation, phi better be real. And we all know that we can restrict to the interval between 0 and 2 pi. The dilation is a real degree of freedom. And let's just take a scaling, and R is a positive number. And the special conformal transformation, let's see. So this just takes a bit of sitting down and doing taking the nasty expression that I wrote above. And here you have an answer to your question, at least in 2 dimensions. B and Z need to have inverse units, like you said already. So Z, and now let's count. Oh, this is not a straight table. Well, anyways, I hope that on your sheet of paper or whatever you're taking notes, you're doing this better. So then we can count the number of real parameters so we have 2 real parameters for one complex translation. We have 1 real parameter in phi, we have 1 real parameter in R, and we have 2 real parameters in B, because B is also a complex number. So in total, we have 6 degrees of freedom. And that is indeed the dimensionality of SO 2,2 or SO 1,3. So that's good. That's sort of what we would have expected. And it actually pays off. So if you zoom in on the dilations and the rotations, so note, you see that you can rephrase them. So the rotation and the dilation can be combined into one complex dilation. Can be combined into one complex dilation. That means if I introduce lambda as r times e to the I phi, that's a complex number. And it's just the product of r and e to the I phi, evidently. Then we can write the rotation and the dilation as z, as mapping z into lambda times z. That's just e to the r I phi z, right? So there is no magic here. It's just a rewriting, which is going to save us some space later, and also just pays off to realize that these 2 rotations and dilations on the complex plane, they're somewhat on equal footing. They have basically the same effect of rescaling a complex number or just changing its angle. Okay, so it turns out, and this is, yep.
Could you repeat why we would have expected the dimension to be 6?
Oh, so let's actually do this. Let's see. So d plus 1 is 3, and d plus 2 is 4, right? So divide by 2 gives 6.
Okay, thank you. Yes.
That's just okay. Thanks for the question. Okay. So one thing that you can show, and this is again another thing that I will just refer you to the literature that I provide in the notes, is that these transformations, so the transformations, actually, let's say the transformations in the table, generate and this is something that is well known to mathematicians, it's called the Möbius group. And the Möbius group, I give an argument in the notes that, actually, let me first phrase the Möbius group, and then I'm going to tell you an argument that you can read up on in my notes or you can just re-listen to this recording. So the Möbius group, basically what it does is it takes a complex coordinate z and it maps it into this quotient. And so A, B, C, and D are taken from a matrix, A, B, C, D, which I call G. And this matrix is taken from the special linear group to C. So these are, that means A, B, C, D are allowed to be complex numbers. In particular, special means that AD minus BC is 1. So that's what it means to be special. And actually, when you look at this, we see that if we take let's make this here, if we take minus A, Z, minus B, minus C, Z, minus D, that equals the same because we can just factor out the negative sign. So we're actually, when I'm taking this group, I'm overcounting, and in order to get rid of the overcounting, I can just mod out. So that's what we say. We ignore this minus sign here. That means we mod out by Z2, which implements precisely this action. This is a Z2. Well, it's not much prettier. Anyways, so this is the Möbius group. The Möbius group is this here, and it acts on the coordinates. So this is how the Möbius group acts on the complex coordinates. So the reason this is fine in CFT, that's what I anticipated before, is that the Möbius group, basically what it does is it takes the sphere and basically just takes the sphere into itself. Actually, that's so we say it's the automorphism group. From what I've seen, you can read up on automorphisms in Pier Alberto Marchetti's notes. But what it means to be an automorphism is basically it's an isomorphism which takes a space to itself, right? So it's invertible. Like a rotation on a sphere, you can always undo a rotation on a sphere. You can undo a translation on a sphere. You can undo dilations, you can undo them here. So they have a very natural place. And it turns out that the sphere S2 is going to be the complex plane that we're working with. And actually what you do is you add to the complex plane a point at infinity. That's to say this point here. It's like you're taking a plane that's sort of like this bottom part of the sphere. My drawings are not very good, I fear, but I'll try my best. And you're adding this point at infinity, which turns it into a sphere. And we're going to be doing this secretly all the time. We're going to be adding the point at infinity. But like I said, go read up the notes if you're interested in the details of this. Okay. So so just a little check. Let's see. We have 4 real parameters. So this A, B, C, D are 4 real parameters. That gives 8. That gives 8 complex. 8 real. 4 complex parameters equals 8 real parameters. Now I get it. So, but now you have also this constraint here, which gets rid of 1 complex parameter. So you again have 6 real parameters. So that's let's just let's make this a comment here. So because of A D minus BC equals 1, 6 real parameters. So that's good. So that's just parameter counting, that we don't do anything wrong. Again, like I'm not really proving to you that this is conform, like these are conformal transformations we're going to see in a minute. But actually, by comparing, you can check that all of these transformations in the table, that they can be written as a Möbius group. So in particular, the following group elements, you can just go and convince yourself to get an idea. The following group elements represent the conformal generators. Oopsie, conformal generators. And those are, for the translations, for those of you who are unfamiliar with this, just go and check this. For the rotation and the dilation, you have this matrix, and for the special conformal transformation, we have, in a sense, if you look at the translation and the special conformal transformation, they're almost transposes of each other, except that you have to adjust A equals B, right?
It should be 1 in the bottom corner.
1 in which bottom corner?
G special conformal. The bottom
Oh,
right
yeah.
element.
Oh, yeah. Thank you. Sorry. Precisely. So you're paying close attention. Very good. Thanks. There you go. So you can just check, those of you who are new to the subject, just go and check that these are indeed, so if you do that, you recovered that from the expression for the Möbius transformation, you just recover the expressions in the table. Okay. So,
sorry, I have a question.
uh-huh.
When you refer to generators, you've also referred it to before. You do not mean like elements of the Lie algebra which give rise to the Lie group, but rather like the basis elements of the group.
Actually, let's be more concrete. Basis. So let's be very concrete. Let's make a new color. So if I have a group, let it be a Lie group. Lie group. That means you have some G in a group G. Then you can rewrite G as the exponential of a sum over some parameters. What do I call them? Omega A, and then something, let's call them the generators, let's call them T. I think this is fairly standard notation in the mathematical literature. So these things, so a Lie group is going to be, for instance, take the sphere. It's going to be some blob like a manifold. It's going to be a manifold, and at a point at the manifold, you can add a tangent space. And a tangent space is a good vector space. So this is the tangent space. And this is a vector space. So on the vector space, there's the notion of a basis. So basically what I'm saying is that these generators are a basis on this tangent space, meaning that starting from this point, they generate any conformal transformation, any transformation. Yeah, let's stick with conformal. But for a Lie group, they would generate any Lie group element. So you, in this sense, I mean a generator. Did that help?
Yes, indeed. Thank you.
Okay, good. So if we want to be pedantic, I think a mathematician, if they hear us physicists speak about a basis for a group, they would probably go nuts. They'd rather like the word of a generator for the Lie algebra. For discrete groups, you don't have this notion of exponentiating, at least not as far as I know. And then you can, however, define generators. So to say, if you have you just make up the smallest set of group elements from which you can reach any other group element, and that's what you would call a generator. But for my purposes, I'm going to be sticking with the conformal group, which is a Lie group. It's in particular, as I said already, SO P plus 1, comma Q plus 1, and so on. Okay. And so it turns out so that the Möbius transformations are well defined, meaning they don't blow up. Well, actually, are well defined everywhere on the Riemann sphere. And the Riemann sphere is what I said before. So this is S2, which is to be understood as the complex plane, oops, not U, unified with the point at infinity. And because they are well defined everywhere here, they're called global conformal transformations. And now in the next step, we're going to get acquainted with transformations which are not defined everywhere on the Riemann sphere. And these are going to be called, in contrast to global, they're going to be called local conformal transformations. But before I go there, are there other questions?
You said that it doesn't blow up, but you include infinity in your possible values. So what's the problem with blowing up?
So let's be very concrete. So the one thing that in which it can blow up, for instance, if you take, given that this is being recorded, let me just make some room here. If you take z equals, let's take minus d over c, then you see that you generate a 0 here. But what that means is that z is being mapped to the point at infinity, which is in the Riemann sphere. In that sense, it sort of exists and it's well defined. Does that help?
Yeah, so I don't understand in which sense it can be not defined, but probably I'll just wait.
Right. So in that's sort of, if we were only talking about the complex plane, not the Riemann sphere, then you would have to exclude precisely this point here. That this point is just problematic on the complex plane because it just goes to infinity, and you need to tell people what you mean by that. And here we have sort of uniquely identified one point, which is like sort of, if you move in one direction, basically in any direction, you'll always get 1 point and 1 point only. That's because we're taking the topology of the sphere. Right? So if I just take the complex plane and I rush off to plus infinity or minus infinity, these are different things. So and I also have to tell you sort of how I go to infinity. Okay. All right, so let's move on. All right, so in 2D, so now comes the important part. In 2D, the conformal group is extended. By that I mean, so I started out with the global conformal group on in dimensions d equal or bigger than 3. Then I talked about the same. Well, actually, I talked about in the beginning about any dimension, also d equals 2. Then I talked a bit about d equals 2 and looked at the transformations that we had for any dimension. And now it turns out that in 2 dimensions, there's something special going on. And that means, or more concretely, that means that the conformal group is extended to be infinite dimensional. Infinite dimensional. And here comes the claim. And the claim is that the set of conformal transformations in 2D, I'm not going to write this, it's implicit, is equivalent to the set of holomorphic and anti-holomorphic functions on the complex plane, or on the Riemann sphere, I should say. So let's think a bit about this. So we're going to start and show. I'm going to start and show that. Let's see which direction I'm going to show. So we're going to show this direction. So we're going to take a conformal transformation. No, excuse me, actually, made a mistake. We're going to show this direction. We're going to take a holomorphic transformation, a holomorphic function, and we're going to show that it is conformal. Oops. Okay. So in order to do that, we're going to use coordinates, which are complex. As before, this is z, but now we're also going to introduce its complex conjugate. And it pays off to know the derivatives. In conformal field theory, it's customary to write only del. So we're omitting the z. We're just writing del, and then for the z bar derivative, we're writing del bar. And this is just what they are. This can be just computed by coordinate transformations. And now we're going to take a map. I'm going to take a map. So maybe, are there any, I'm not sure if it's good to ask, but if there's somebody here that I think it's a small enough circle, who is not super duper familiar with complex analysis, just feel free to ask questions. I'm afraid that I didn't prepare much on like the topic of how to use like how to derive complex analysis, but how to use it. We're going to use it often here, so it may pay off to refresh that. Anyway, so we're going to take a map on the complex plane, which we can decode into reals, meaning that it has a real part and an imaginary part, which I'm just going to write as W0 and W1, just as we did for the coordinates. And then there's also going to be its complex conjugate. 0 minus, where the functions W0 and W1 are real. And then, and here's something where I'm just going to assume that you're sort of familiar with this. I hope that you are. If you're not, I can actually, so for next time, I could try to prepare a little bit of complex analysis. Holomorphicity, let me just say, there's something called the Cauchy-Riemann differential equations. I'm going to abbreviate differential equations by DE. Basically what they mean, if you take the maps that I have written above, they mean this relationship. It's a constraint. And the constraint is that W bar, the derivative, the del derivative on W bar is 0, and the del bar derivative on W is likewise 0. But this is important. What this means is that W bar, even though we set out with W bar as being a function of Z and Z bar, is that W bar, if it is holomorphic, or actually anti-holomorphic in this case, is only a function of Z bar. By anti-holomorphic, I mean a function of Z bar, and by holomorphic, I mean that W is actually only a function of Z. So in the future, whenever I say a function is holomorphic, I mean it's a function of Z only and independent of Z bar. And vice versa, when I say a function is anti-holomorphic, it's a function of Z bar only and independent of Z. Okay. So if this is the case, then these mappings here, actually, let's make this more concrete. So Z bar is being mapped into this, and here the same. This means that the maps actually, so Z, we can make it sort of independent. Z is being mapped into a function of WZ, while Z bar is being mapped into a function W bar of Z bar. This is what it just means to satisfy the Cauchy-Riemann differential equations and what it means to be holomorphic or anti-holomorphic. And that means that DZ transforms very simply as so the differential form DZ transforms simply as a one form. Well, it always has a one form, but it just rescales. That's the point. And DZ bar equally rescales. Okay, so one thing that you can do, if you take the metric on the complex plane, the metric on the complex plane is DZ bar up to up to prefactors. So in the notes, I am actually a bit more pedantic. So these things are tensor products and they don't commute, but the result is all the same. So now if I do a coordinate transformation, what I pick up.
Christian?
Yep.
You have a bit less than 10 minutes left.
Thank you. Bit less? Wait, a bit less?
A bit more, sorry, a bit more. Yeah, okay, a bit more.
Yeah, no, but maybe I should quit. Like I will, like in 10 minutes, maybe remind me, and then I will just ask for questions. That'd be nice. Thanks.
Okay, we'll do.
Right. Okay. So the metric, you just see that you pick up. In particular, one thing that I'm going to use is that these things here are complex conjugates of each other. So you pick up the absolute value of the absolute value of the Jacobian between the in the coordinate transformation, and this is a real function. It's positive, so that's just a scale factor, meaning that we have found a conformal transformation. Oops. So this is a conformal transformation, and therefore we have seen we have found that at least one direction of the claim that I made before is satisfied. Okay. So now you may ask about the inverse direction, and I hope you do, and it's actually left for you as an exercise. So in the notes, that's exercise 3.1, where you show the other direction. I have worked out all the solutions to the exercises, and I'm happy to discuss. But I still have to figure out how, if at all, how I'll distribute these solutions. I think this is also that I will discuss with Saskia and friends, like with the school itself. Okay, so this makes for a powerful claim now. So let's just recapitulate. So let's just make it a sentence. So in 2D, the conformal group is the set of all holomorphic and anti-holomorphic Oh, and if you can't read anything, please let me know. You shouldn't, like, it shouldn't be like that should be the least of the problems. I'll try to write cleaner. So anti-holomorphic maps and group multiplications are just the standard, or group multiplication is the standard, is the composition of maps. Okay, so that's the conformal group. So in particular, let's see, how much time do we have left? Let's make a few remarks. So remarks. So the Möbius transformations that we discussed before are a subgroup. Well, the argument is simply that Z takes AZ plus B into ZZ CZ plus D. That's just Z becoming another function of Z. This is sort of like W of Z, right? So that's a holomorphic map. And there is another comment which is usually swept under the rug. Some sources do mention it though, that we actually are going to allow for meromorphic transformations. Meromorphic transformations. Don't be scared by this away. So the word meromorphic, what it means, these are functions with countably many singularities. Countably many singularities. For instance, the inversion, it's like Z goes to 1 over Z, stuff like that. Basically, one, like we already have this here, this is on the Riemann sphere, but we're going to allow for more, meaning that we're also going to allow for Laurent series. So if you just have a holomorphic function, these things are in particular, we say analytic, which means you can expand them into Taylor series. And when they're meromorphic, you call these series Laurent series. And they are not going to be well defined. Defined on the Riemann sphere. Everywhere, not going to be well defined everywhere. They're going to be well defined mostly on the Riemann sphere, but they're going to have points where they're problematic. Not well defined everywhere on the Riemann sphere. Riemann sphere. S2. And that's why they're called local conformal transformations. Okay, let's see. Now we have, actually, let me make one more comment, and I think that's a good point to stop. So this is a bit off topic, but it's a good point to make this comment. Usually, so the coordinates z and z bar are treated as independent in CFT. Independent in CFT. And you will say, well, that's odd. And it is odd. So the way you should think about this is that you take the real complex coordinates x0 and x1, and you complexify them. So you complexify them first before combining them into complex degrees of freedom, which means that you now have 4 real parameters. Let's call them DOF, 4 degrees of freedom. And then just reshuffling them into complex coordinates is just a rotation. It's just a coordinate transformation. And then at the end of the day, at the end of every calculation, well, not every calculation, but let's still write every calculation which leads to some physical result. You should restrict to what's called the physical or the real surface. Let's make another color. Physical or real surface. And by that, I mean that z bar is to be taken as, and now I'm going to sort of, whenever I mean complex conjugate, from now on, I'm going to mean the star. And whenever I mean z bar, I mean the independent coordinate z bar, independent of z, unless otherwise stated. Okay, so far so good. I think we're going to leave it here. Next time, I'm going to talk about the generators of the local and the global conformal algebra. And we're going to get an idea of what it means that these things are not defined everywhere, or that they are defined everywhere. We're going to talk about the Witt algebra. We're going to talk about the Virasoro algebra. And maybe we'll even get to talk about fields already next time. But for now, I think it's a good point to stop. And if you have any other questions, please go ahead.
Maybe, okay, thanks, Christian. So tomorrow, Christian, you have Christian back again at 2 p.m. with the rest of this lecture. So let me suggest the following. Next time that you log in, can you please put your full name, or at least something that I can see a full name, so it's easier for me to accept people from the waiting room. This lecture is being recorded, So now, so that people can ask questions now if they want. I will stop the recording, and the recording will appear on the YouTube channel of the cost action, but you will receive all the links. That's all. So now I will stop the recording.